Hello student, welcome back to A-Star Tuition channel. Today we will discuss about circular motion and gravitation. Let's start. In this part of the video, I will only discuss about circular motion so that it can lay some foundation later when we discuss about gravitation. Now, I mentioned briefly in the kinematics video that we discuss about one-dimensional motion. However, in the third part of the video, I did mention that we discussed about the projectile motion, which is two-dimensional motion. But projectile motion is not the only two-dimensional motion, because there's also circular motion. But this actually need to be treated a bit differently, because we need to understand forces first before we do. Now, imagine that a particle is moving in which the path of motion is a circular one. Yeah, so it follows a circle and it can move either clockwise or counterclockwise. Yeah, so let's just make it, in this case, counterclockwise. So you can see that the particle is moving from this point to that point, and you can see that the velocity is always changing. Now, what I mean by the velocity is always changing is not necessarily because it's getting faster or speeding up, or it's getting slower or slowing down, but just the fact that the direction of motion is always changing. Now, let's take a look at, like, for instance, when the particle is at this point, at the bottommost position, it has a velocity that is going to the right, like this. However, once the particle reaches this point, you can see that the velocity is now directed this way. And the factor, this factor and this factor, are different, even though the magnitude could be the same. Alright? Now, but that is not the same velocity because of different direction. Here, the velocity is constantly changing. So remember when I mentioned about particle that undergoes change in velocity, that means there must be an acceleration. Now, the type of acceleration that we discuss is actually a bit different from the one that we usually deal with in either kinematics or the dynamics. I will discuss about that later, but first let's talk about some of the kinematic quantity related to circular motion. Now, as I mentioned previously, that the speed is assumed to be constant. Yeah, so but that the velocity is changing because the direction is changing. Now, when the speed is constant, we call the circular motion as uniform circular motion. That is, it has a constant speed and a fixed period. Now, obviously, not all circular motion is uniform, but we start from this discussion because it's the simplest discussion and it appears to be the most occurrences that you will encounter in this topic. Okay. Now, constant speed. Constant speed means that the speed here equal to speed here and elsewhere. So that it has a fixed period. What is period then? Well, the period is actually the time it takes for this particle to move anti-clockwise around the circle once and back to the original point. So the time is called period. So we can now define the period as the time to complete one cycle. So one cycle is defined as the process of completing one circumference of the circle. Okay, so that's the time period. Now, how do you actually calculate this time? Now, in order to do that, let me remind you that one circumference of a circle is given by 2 pi r. This is the circumference, right? Circumference is equal to 2 pi r. So in one period of time, the particle travel a distance of 2 pi r. So the speed can be calculated relatively straightforward by using distance over time. Remember, because this is motion with constant speed. Now the distance is one circumference, which is 2 pi r, and the time is one period, capital T, and the speed is equal to v. So from here we can say, okay, you can calculate one period as 2 pi r divided by the speed. So this is the period. Now there's also another quantity that is related directly to period, which is the frequency. So frequency is simply how many one complete cycle that is traveled or that is completed in 1 second. So how do you find frequency? Now, because period is the time to complete one cycle, so in order to find how many cycles during one unit of time, the idea is just to take the reciprocal. So then the frequency is simply equal to 1 over the period. Yeah. So let me give you example so you can understand why this is true. Now imagine that the period, yeah, t equal to 5 seconds. What does it mean? It means that in order to complete one cycle, the time taken is 5 seconds. Now, let's say that this particle is completing one cycle in 5 seconds. So we say that the period is 5 seconds. Now, the question is, how many cycles that is completed in 1 second? Now, in order to answer that, let's look at this. It says that we require 5 seconds to complete one full cycle. So then the question is, how many cycles in 1 second? Now, in order to answer that, all we need to do is to divide that with 5. Yeah, so because 5 seconds is to complete one full cycle, so therefore in 1 second it only completes 1/5 of a second, 1/5 of a cycle. So the frequency is f equal to 1 over 5. So there are 1 over 5 cycle per second. Okay, and this second minus 1 can be written as hertz. So this is 1 over 5 hertz. Now hertz is actually another unit here for frequency, which is equivalent to s2 power minus 1. Another example would be, let's say that the period of a circular motion is equal to 0.5 seconds, which means that it only takes half a second to complete one full cycle. Now, so the question is, how many full cycle, how many complete cycle in 1 second? So, because it takes only 0.5 seconds to complete one full cycle, then in 1 second there would be 2 full cycles. So in this case, the frequency, which is the number of complete cycle in 1 second, is 2. So 2 full cycle per second, 2s minus 1. Now s minus 1 is hertz. So the frequency is 2 hertz. So this is the explanation or illustration, I should say, of how a period is related to the frequency. It's only the reciprocal. So the period is the reciprocal of frequency, and the frequency is the reciprocal of period. So therefore, this explains this equation. Now, so far we see that there are linear quantities that we discussed. So the linear distance, and also the radius, and also the speed, linear speed. Yeah. But what about the angular quantity, like theta? Now, in math, you learn that in circle theorem, if the theta is given in radian, then you can actually find s by using this equation, s equal to r theta. Now, the reason it works is this. Yeah, remember, this is like the arc length of part of a circle. that is associated with angle theta. Now if theta is 360 degree or 2 pi radian, then S would have been 2 pi r. So, but then if the theta is not 360 degree or not 2 pi radian, then you can calculate the S by using whatever the theta is in degree over 360 multiplied that by the full circumference, which is 2 pi r. Now, this is when the angle theta is given in degree. However, if the angle theta is given in radian, then we replace the 360 with 2 pi radian. So the S becomes theta over 2 pi times 2 pi r. And this cancels, so it gives you S equal to r theta, which is this one. Yeah, so the theta here is in radian, so therefore we use the relationship S equal to r theta. Now, we assume that the radius is fixed. Now, if the radius is fixed, then we can actually find the relationship between the angular quantity and the linear quantity. Not only the distant travel, but also the angular distance or the angular displacement that is covered during the motion. Now the speed here is the rate of change of the distance travel. So that V is equal to delta S over delta T. But then the S is r theta. So this is delta or r times theta over delta T. However, if the radius is fixed, we can actually pull it out and then write it as r times delta theta delta T. Delta theta delta T is the rate of change of the angle, the angle covered during the circular, during when the particle is moving circularly. Now, this quantity has its own name, and we call it the angular velocity or angular speed, and it has a symbol of omega. So it looks like W, but actually this is a Greek letter omega. So delta theta delta T is the angular speed. So you can see that there is a relation between the linear speed and the angular speed, which is actually similar to this one, but this one is relating between the angle that is covered during the circular motion and the linear distance travel, whereas this is the relation between the angular speed and the linear speed. Yeah. Now, what is angular speed? Now, from the way we define it is about how much angle travel per second. Now, since the motion is uniform, that means the amount of angle traveled in 1 second or in any time will be the same for the same time, which means that we can actually find the angular speed by using the complete cycle. Now, in the complete cycle, the angle covered is 2 pi radian. And the time is 1 period. Remember, the period is time to complete 1 cycle. So therefore, the omega simply 2 pi over period. Now this should be not surprising, shouldn't be surprising, because when you look at the equation, see, this is 2 pi r over t is phi, and omega is 2 pi over t. Now here, if I were to not split, but then to group this expression 2 pi over t times r equal to phi, then you know this is omega, and what we got is omega r equal to phi, which is something that I already discussed here. So it makes sense that omega is 2 pi over period. In other words, it tells you how many radian travel per in 1 second. Yeah, so omega is the angular speed, v is the linear speed. So earlier I mentioned that even though the motion is uniform circular motion, which means that the speed doesn't change, but the velocity changes continuously because the direction changes continuously. So if there's a change in velocity, there's always an acceleration. So how do we account for the acceleration in this case? Now, in order to answer, let's show how to find that acceleration. Now, look at this. Here at one point, initially, let's say it's at this point and the velocity is vi directed to the right. And then at some point later, sometime later, it is at this point and the velocity is vf. So there's a change in velocity. Remember, how do you find change in a vector quantity? Change in vector quantity, as we discussed in the vector video, delta v in this case equal to v final minus v initial, which is equal to v final plus negative v initial. Okay, so then you have a vector vf going this way, and then minus vi. Okay, so minus vi going that way. Now remember that vf and vi, they both have the same magnitude. Yeah. Oops, sorry. This is supposed to be. Sorry, let me redraw it. So this is vf, yeah, about this length, about this long, and then here this is vi. So this is minus vi minus v initial, and this bit is v final. Okay, so v final minus v initial. So therefore, the change in the velocity factor is this one. Yeah, from you draw a line from the tail of the first factor to the tip of the final factor, and this is what you wind up with. Make sure that this is equal to that in terms of length. Now you can see that the delta v is directed to the center of the circle. In this case, if you were to move vi here, so let me redraw this situation here. So this is minus vi, yeah, and then vf minus vi gives you this. So it gives you direction that is towards the center of the circle. Now this change in velocity, the change in velocity, which is directed towards the center of the circle, is the type of acceleration associated with the change in direction. Now we call this velocity, the change in velocity is tangential, not tangential, but a normal change in velocity. Normal because it's perpendicular to the motion. Look at this, it's perpendicular to the path. And the associated acceleration is called the centripetal acceleration. Now how do we account for this centripetal acceleration? Now remember that acceleration can be found by delta v over delta t. But remember, we don't want to find the average value, we want to find the instantaneous value. So then we need to find this expression with the limit delta t approaches 0. So remember, for instantaneous value, because we want to calculate the acceleration at one particular time, anytime, we need to make sure that the time interval is so short. So in other words, vf is very close to vi, the tip, the tail of the factor. So it's like very close. So in other words, the delta theta approaches 0 as well. Okay, so let me explain to you how to find an expression for this instantaneous acceleration. But I also need to tell you that it is actually not necessary for you to understand this derivation. But perhaps if you understand the derivation, it will be easier for you to convince yourself that the equation is indeed valid. Okay, in order to do that, now let's redraw this diagram here. So you have this, let me just change the orientation a bit. So let me just, rotate like this so you can see. So you have minus Vf going this way, minus Vi, sorry, and then Vf going this way. So because the two have the same magnitude, we have an isosceles triangle. Yeah, so then here, delta V would be this bit. This is delta V. Now, in order to find the magnitude of delta V, this angle theta here is actually also the angle between this and that. Yeah. So whatever the change in delta theta, remember we make the theta close to 0, so delta theta close to 0. So like, because this is delta theta, and this is Vf, this is Vi, then the angle between the two is also equal to delta theta. Yeah, remember, from Vi to Vf. So then the angle has changed by this. So this is delta theta over here, right? Now, if I were to draw a line perpendicular from this point to the other side of the opposite side of the triangle, then you can see that the angle is now bisected. So then each has magnitude delta theta over 2. Now, this bit, if I multiply delta theta over 2 with Vi, the magnitude of Vi, remember, magnitude of Vi and Vf is the same, yeah, which is V, which is the speed, the constant speed, yeah. So then here it has a magnitude of V sine theta over delta theta over 2, and then here also the same, V, because of symmetry, yeah. So then you can see that delta V, the change in velocity, has a magnitude of twice of this, so 2V sine delta theta over 2. Okay, so this is delta V. Now remember that A is delta V over delta T. So in order to find the magnitude of A, all we need to do is we do magnitude delta V over delta T. Okay. Now, the delta V has a magnitude of 2V sine delta theta over 2. And what about the time? Well, remember this S over here is equal to R theta. So then delta S equal to R delta theta. The reason I changed the notation from delta S, from S to delta S and from theta to delta theta, because we want to calculate the amount of change, yeah? The change in S, the distance traveled during when the velocity changes from Vi to Vf, and delta theta is the angle traveled during that change. So here delta T would be, delta T can be calculated by using this, yeah. So delta S, delta T is the time, so time is equal to delta S over delta V. So delta S over V. Okay. Now delta S is equal to R delta theta. So you have 2, the V moved up, become 2V squared sine delta theta over 2. And then you divide it by delta S, which is R delta theta. So now, when we have this expression, we can do a bit manipulation. Sine delta theta over 2. We can just bring the 2 down here, so it becomes the denominator of delta theta, so delta theta over 2. Now the reason we do this is because you have sine of an angle divided by that angle, so it's like sine of x over x. So sine of x over x is an algebraic expression, Now remember, this algebraic expression is taken when delta theta close to 0. Now so then when the expression of x, sine of x over x close to 0, the limit of that expression becomes 1. Yeah, so this is actually not something, maybe some of you probably know about this, but even if you don't, yeah, this is a simple, a straightforward fact that you can check. So when you have an expression x, and x is approaches 0, x approaches 0, so sine x over x will approach 1. So therefore, it will give this remaining expression sine delta theta over 2 divided by delta theta over 2 as 1. So it will become p squared over r. So in the limit of delta t approaches, remember, delta t approaches 0, that means delta theta approaches 0. Because remember, it has a finite speed. If it has a finite speed, then that means the angular speed omega is finite. So if the delta t or the time interval is close to 0, then that means the angle travel will also close to 0. Yeah. So in that case, the limit taken when delta theta approaches 0, then the expression sine delta theta over 2 over delta theta over 2 will also will become 1. Yeah, so it will equal to 1. So then this expression will give you this acceleration, and this acceleration is what we call as the centripetal acceleration. So this here is the centripetal acceleration. So remember, as an acceleration, it has magnitude and also direction. Now the direction is the same as the direction of delta phi, which is going into the circle. So in other words, the centripetal acceleration at any point is always towards the center of the circle. So it's always towards the center. In other words, let's say the particle is now here. If the particle is here, then the direction of the acceleration is this way. If the particle is here, then the direction of acceleration is this way. Now you can see that the acceleration itself will have different direction every time. Yeah, so this direction is not the same as this direction. Yeah, but regardless, it will always point towards the center of the circle, and we call it centripetal acceleration. Next, we'll discuss some scenario in circular motion, so you can see how to solve problem related to circular motion. Let's look at this scenario. So imagine that you have a particle, like maybe a small rock, that is tied to a taut string, in which the string is continued through a small hole on top of a table, and that the string is pulling the rock, but then the rock is actually still moving. So let's say it's moving clockwise like this. Yeah. So then the top view of this situation would be this. So then you have this rock over here, let's say. Yeah. And this is the center of the circle, and there is a force acting. Now you can see that this force is the tension and is directed towards the center of the circle. Now there is no other, well actually there's two forces. The normal force from the table to the rock, and also it's the table's own weight, the weight of the rock. But since the rock is constrained to move on the surface of the table, these two forces cancel. So the only force acting is this, and this is directed towards the center of the circle. So then we say that this tension acts as the centripetal force. So in other words, this is what provides the centripetal force. By the way, I want to also remind you something that is quite important. If a question asks you to draw the force diagram for the particle in this situation, in this scenario. By the way, if there is a question asking you to draw force diagram for this scenario or this situation, do not draw centripetal force on in addition to the tension, yeah, because this would have been wrong, because the only force acting is tension. So then tension is what provides the centripetal force. So the nature of the force, the nature of the centripetal force is tension in this case. The reason why you shouldn't include Fc here is exactly the same way, the same reason why when you do sigma F ma in the problem, you do not include the F in the equation. So only, let's say, T and let's say friction. So T minus F. And then you don't add F, right? So this F is already appear here. So you don't do that. Similarly, in a circular motion, Fc is just the sum of all forces that is radial. So whether it's going into the circle or out of the circle. Now in this case, there's only one force acting, which is the tension. Later we will see some other cases in which there are two forces, one into and one out of the circle. So Fc, or the centripetal force, is simply the sum of all radial forces that is responsible for the circular motion of the particle. In other words, responsible to change the direction of the particle in the motion rather than the speed itself. Okay, so I hope you understand. So in this case, we write down the sigma Fc. Oops. We just use this sigma Fc equal to T. So that's the only force that is radial and is directed towards the center of the circle. And this is equal to m v square over r. Yeah, remember, the acceleration is v square over r. So from here, we can see the relationship between tension and mv square over r. Now, by the way, I just want you to understand, sometimes we inadvertently use the same symbol for different quantities. Now, remember earlier, for period, I used capital T, but in this case, the tension is T. So maybe I should change it a bit to Ft, yes, the F tension, so that we can make use of the, we can make use of capital T as the, the period. Yeah, so, and remember, the omega is, V is omega square r. It's omega square r square, because you squared. Yeah, so here m omega square over r, m omega square r equal to the tension. And because omega is 2 pi over the period, yeah, so then we can actually calculate for the period by rearranging. So Ft over mr, if you take the square root, that's equal to 2 pi over period. So the period is equal to 2 pi times mr over Ft square root. Now, so then you can find the period of the motion by simple analysis of and the application of mv square over r equal to the resultant forces that is radially inward and outward. Now in this case, there's only one radial force, which is the inward, the tension. Now let's consider a horizontal pendulum. What is a horizontal pendulum? So in this case, the pendulum is not swinging like this. This is called vertical pendulum, but it's actually swinging like this. So the circle that follows the tip is a horizontal circle. So like this. So then here hopefully you can see the perspective drawing. This is the path of motion of the particle that is tied to the string like this, and the circle is horizontal. Okay. Now, when you look at the force acting, this tension here is directed at the angle with respect to vertical. Now, what we want is we want to find the force that is towards the center of the circle. But actually, that can be easily done by resolving. Remember, we learned about resolving factor. So in this case, the T here has a horizontal component of T sine theta, because it makes use of the opposite side of this triangle. And then the T can also be resolved vertically, and it will give you T sine theta, T cos theta, yeah, T cosine theta. Okay, now the T cosine theta, you know what, let me just again use Ft instead of T, yeah? F tension, because I want to use capital T for the period, so that to avoid ambiguity. So Ft cos theta, Ft sin theta. Now the Ft cos theta must equal to the weight of the particle. The reason being, the particle actually doesn't move vertically up and down. So it's vertically it's the equilibrium. So the sum of the vertical forces Ft cos theta minus mg equal to 0, which means that Ft equal to mg cos and Ft cos theta equal to mg. Yeah. Now on the other hand, this Ft sin theta here is directed towards the circle. It's radially inward. So that is actually that is what acts as the centripetal force for this case. Yeah, so we say that Ft sin theta is equal to m times v squared over r. Now we can do some manipulation algebraically by dividing these two equations, in which case the Ft and the Ft cancels. They cancel, and you only have sine over cos, and sine over cos is tangent theta, and the mass and this mass also cancel, and you're left with v squared over gr. And from here, if you want to calculate the period, again use v equal to omega r, and we can write down omega as 2 pi over period. So tangent theta equal to 2 pi square, which is equal to 4 pi square times r square over, there's t here, t square, and then you have gr, and the r can cancel, and then from here you can say, okay, so then the period t square equal to 4 pi square r over g tangent theta, and then from here you can find the period to be 2 pi square root of r over g tangent theta. Okay, now if you want to calculate the amount of tension, then you can obviously, once you solve for any one of these, so once you solve for theta, you can solve for the Ft using one of these equations. So this is the example of horizontal pendulum. Now for the case of the vertical pendulum, is actually not uniform. Yeah, the reason is because the movement from one point to another point, like from here going to here, the speed is not going to be constant. Yeah, because if the pendulum only swing through this angle, so it stopped here, right? But then here it moved the fastest, later it will stop. So then you can see that the speed is changing. So it's no longer uniform. But you can still use the equation for the centripetal force equation in this case. Now, one particular case that you can consider is this. When the particle is at the lowest point. Now at the lowest point, you see that there is tension here, the force of tension upward, and this is the vertical pendulum here. The force of tension upward and the mg downward. Now in this case there are two forces, two radial forces. One is mg and is directed, outward from the circle, and Ft is directed towards the center of the circle. So in this case, if you have two forces, two radial forces, the way you write sigma F is you always use positive sign for the force that is directed into the center of the circle. So in this case Ft, and you use minus or negative sign to the particle that is directed away from the center of circle, which is mg. So this would be mv square over r. Now, since at this point we know that it's moving at this with the largest speed, because remember, since the pendulum only swing this far, that means at this point and this point, the extreme position, it stopped. But then at this position, because the kinetic energy is the fastest, because the potential is the lowest here, then that means the speed here will be the largest. Now if the speed here is the largest, so it's non-zero, so that means the sigma f is non-zero. Now when it reaches this position, the maximum position, the resultant force also non-zero. Now we will actually discuss a lot more about this when we discuss about simple harmonic motion. But for now, all I can say is that the particle that is swinging in vertical pendulum that lasts indefinitely, this is an example of a motion in which the particle is never in equilibrium. It will never be in equilibrium because the resultant force is never zero. It's not zero here, it's not zero here, it's not zero even in the middle, because you can see that the resultant force is non-zero. Now last example I want to discuss about is the motion of roller coaster, in which there are actually two different scenarios you need to consider. When the roller coaster is at highest position, but that the position is such that the roller coaster is inside the track, so it's the inside track. So whereas this one is the roller coaster that is located outside the track, like this. So hopefully you can see the difference. Now the difference is that from the force diagram, these two forces N and mg are both directed towards the center of the circle. So we write the equation as sigma fc equal to N plus mg, because both are directed towards the center of the circle, equal to mv square over r. Whereas for this one, the normal force is directed away from the center, but the mg is towards the center. So then in this case, sigma fc equal to mg minus n. So remember, mg is downward, but n is upward. But then usually we use upward as positive and downward as negative. But then here, remember, in circular motion, the resultant force that we use, the resultant centripetal force, the convention is that all forces that is radially inward is given inward towards the center of the circle is given a positive sign, and that's the case for mg, because remember, at least part of this trajectory is circular. So then the center of circle will be here, so mg is towards that, so it's given positive sign, and n of the normal force is radially outward, so away from the center of circle, so it's given negative sign. And again, this is equal to mv square over r. So similar but a bit different. Look at the sign. So here the roller coaster is at the track, but then it's inside, whereas here this is outside. Now, one last thing that I want to also mention is that there are also questions regarding what is the condition in which the roller coaster can safely travel through this travel to the track like this, so that there's no, so that it's safe. So it's safe to make the turn in which at the highest point there is no incident happening. So that no unwanted incident. So what is the condition for that to happen, for the safe turn? Similar to this one, what is the condition upon which the roller coaster or the car of the roller coaster can safely move through the track without ever losing contact. Now, so we mentioned about the contact, so it shouldn't lose contact. So once it loses contact, then it's not safe. So in other words, in this case, what you need to understand is that in order not to lose contact, then the value of the normal force should be a positive number, or at least 0, the minimum. So then we set 0 as the limit, the lower limit. So in this case, the n must be greater than 0, yeah, in order for safe turn around the track. Yeah, so in this case, in the case of for the roller coaster inside the track, the n greater than 0, but then remember n plus mg equals mv squared over r. So then we can write down mg, we can write down n equal to mv squared over r minus mg, and that the n must be greater than 0. So in other words, this n greater than 0. So v squared over r minus g, I can just, get rid of the mass, yeah, because, okay, let me just move this to the other side. Let's move mg to the other side, and then cross m. So the v squared greater than gr. In other words, the v must be the minimum, yeah, must be root of gr. So meaning that if the speed at this point is less than gr, then the ride is not safe, because there will be no normal force. So then it will lose contact. If the contact is lost, then obviously the car here will not be able to maintain in contact with the track. So it's not safe. So this is the minimum. So it has to move fast enough in order for that to happen. Now what about the case of the roller coaster outside track? Again, for the safe turn around the track at the maximum position here, the normal must be greater than 0. So n again must be greater than 0. Now what is the equation for n for this one, for this case? Now in this case, mg minus n equal to mv squared over r. So you can write down n as mg minus mv squared over r. And this must be greater than 0. So mg greater than mv squared over r. So g greater than v squared over r. Or in other words, v squared is less than gr. Okay, so that you can see that this is kind of similar, only the inequality sign changes. Yeah, so in this case, this would be the maximum. So it has to be less than, v squared must be less than gr. So it cannot be more than. So then the v has a maximum value of root of gr. So they both, at least numerically the same. The expression is the same, but then this actually, for the case of the roller coaster in the outside track, this is the maximum value, because if it travel too fast, that will lose contact. Whereas here, if it travel too slow, it will lose contact, and both are not safe. So I hope you understand this scenario in which you have two different situations in which the roller coaster of, the car of the roller coaster is traveling at the highest position. One is inside, is in the track but inside, and the other one is outside. So that's it for our discussion regarding circular motion. We will continue the discussion about circular motion in the context of gravitational field. So I hope this video helps you understanding the basic concept of circular motion. Please like, subscribe, and share the video. I'll see you again later.